Здравствуйте. Я буду, наверное, говорить по...
Hi. Russian is my native language, so let me speak Russian. I know it better, I guess, though I worked in many places. And the project that I want to tell you about is OpenDataPlane. Is the project for network acceleration and for the use of data plane and unification of API in data plane. So at this conference, we heard a lot about the routing protocols and the communication protocols. And my project is around this systemic level of packets and data plane. So if we simplify any network application, it's some packets come from the network and the driver accept them, application processes, and send them further. Looks simple. In the internet, I tried to find a picture how it is made in Linux core, and I found approximately this picture how it is made. I realized, so when the packet comes, it follows the whole long chain. So first the hardware interruption, then software interruption, then sockets, and then the system of requests. And that's a long chain. Then speaking about the development of the network, we can speak about two tiers: data plane and control plane. So sometimes three levels: control and management plane. So data control and management, but mainly there are two main levels where data plane renders all the heavy work for quick transfer of packets to forwarding and modification, and control plane is in charge of setting routing protocols, spanning tree and other steps. If we look at the, that's my previous presentation. I did not delete that. But if we want to process network packets in the application, software application, we can approximately estimate the time that we have to process the packet to send it further. And it's easy to calculate. If we have a processor, 1 gigahertz processor, then approximately one cycle, so one instruction of the processor is 1 nanosecond. If we have traffic of 100 megabit a second, we get 6,700 nanoseconds. And if we accelerate the network, we only have 6 nanoseconds to process one packet. So we have to process, modify, and send further. So we need to raise the processor speed, or use several processors or some other hardware accelerators in order to process the traffic. Why we should not process in the kernel? At least we can, but why not at high speed? First, we lose in latency. In order to receive the packet, the kernel, the driver, is waiting for an interruption. When? We don't know when it will be interrupted, but processor may process other interruption, and they may be switched off. And switching the context from application to the kernel to load the driver takes some time, and the size of the structure that keeps the packets is several kilobyte, and several kilobyte is several cache lines in the processor, and it will add up to the kind of current expenses. And if an application fails that is active. In order to restart the system, we have to restart the application. But if we copy the application into the kernel and the kernel fails, we need to reboot the whole host. Even if it is virtual, then it's not easy or fast. I'm not going to read out the whole list. And use of hardware accelerators. Data plane can be defined or break down into types. Completely hardware data plane that's made in a crystal FPGA chip. It may be completely software like DPDK. We receive packets and through some software logic send further, or software defined when we say, yes, we shall process by software, but if we have hardware accelerators on the platform, please, let's use them. And I guess that's my main takeaway. And it shows two levels. The bottom level with the vendor, hardware vendor and the processor vendor, and the upper layer with the application suppliers. And OpenDataPlane should be the merging node of the hardware vendor and the application developers. So it should be somewhere in between, because hardware is very complex. If we take SDK of cover Broadcom Tilera, and you have application written for that SDK, so changing your application for another vendor is a very effort-intensive exercise. Even if the vendor brings you a board and say, I have SDK documentation, please try to solve it. You will spend some 3 months just to launch it and write some tests that might match or might not. But if you have a standard API, you can take your application for one vendor and just migrate it to another platform. OpenDataPlane is an open source project on GitHub. It's placed on GitHub in Linaro directory /ODP, where with the definition of API and reference implementation is also there. That's what you can take the library and cases and launch it at any Linux through roll sockets, for instance. And then there is two types of library, static or dynamic. And ABI compatibility mode support. If your application uses ODP library in API compatibility mode, you don't even need to recompile your application in order to switch to another platform, to migrate it to another platform. It should work as it is, or probably in non-binary compatibility mode, when we use native types of the platform that you have, and then we achieve the best efficiency. And in the repository, there are tests to check the API working properly, cases, because examples and documentations. What are the other data plane examples? For instance, DPDK, NetMap, pfring, and they all allow you to receive packets into the application by passing completely the network stack of the operation system. But these applications are more matching the network cards. ODP on the whole is not for only for network cards. What's the trouble with network cards? When we receive packets on network cards, we virtually perform DMI, direct memory access transactions, DMA transactions. If we have many small packets, we can calculate the PCI speed. And many small packets will just clog the PCI channel. And the throughput will be hurled by the PCI bus. And it's either you will have to group packets in some way by groups, like Chelsea does, drivers do, and just push them, squeeze them through into the operative memory of the host, but then you lose in latency, and or just push them one by one, but then you lose lose the throughput. And the system on Crystal processor for the network looks like that. It is a bundle of processors, and standard ports, input out memory timers, and they have network accelerators like classifier, scheduler, hardware scheduler, traffic manager, and others. ODP consists of the components. From left to right, we can see the abstract level, the packet input. Packet input we call any abstract thing that the library can provide. It may be network card TH0, or some may say that's shared memory, or some other input, or DPA, or a bus like Freescale. And the classifier is a block that breaks down the incoming traffic to queues, then schedulers, threads, traffic manager, and some other blocks that accelerate the network. And the normal launch model run model is ODP. ODPDK are similar. It's one kernel that's the control plane. We call it a control kernel, and other kernels are just run in busy loop and process the whole traffic. Then I'll tell you about the software part, because I'm a software guy. Packet input is made like an abstraction as well, ODP, EOT packet. Knowing about this abstraction, you can always set it up, and there's a special interface if we take the start-stop statistics and promise mode and things, and then we have ODP, packet T abstraction. So this is an abstraction of network packet. When ODP works with the packets on the software level, it works. It works with packets, and it can be fragmented, and it may be a separate. Because it is hidden behind the deployment. And then some processors use the hardware queue, because the packets queue, and the application reads them from the queues. And then the queues may be different. So some support the continuity, some don't support the queue. It's all described in the implementation. And there are several working modes and accounting for the packets. For instance, so that's when we make queues and say, I want to read them in the incoming queue, and then send them to outgoing queue. And then when we use a hardware scheduler, we say, is there any event? The scheduler would say yes. What kind of event is that? It's an event when this network package comes, and I say yes, then I do something to this packet. It may be some timeout, that may be some return from the finished crypto session. And so the packets are stored in memory. So it's a buffer where we keep packets, and they queue.
Определяют классификатором.
And this is the thing that is behind at the entry when you get the packet. We program it with special rules, and thus the traffic will be going into flow. So then RSS rules or just better, more smart rules. The traffic manager is something that was on the right-hand side at the exit. So after it's been processed, the manager so is responsible for the quality of service, and it's designed in a way that the programs they have nodes, and the nodes have the special type. It's assigned to them, the throughput, and eventually all this looks like this. So these things come to nodes. The nodes organize policies, and the policies go as nodes, and so then COS is tuned, and some packets dropped along the gloss algorithm, WL algorithms along these algorithms. Then encryption. In encryption, ODB supports encryption. This slide shows that, for example, if there is a packet coming, goes into the classification, then the ODP thread, then we receive it. So it's encrypted. We understand that it's encrypted. Then we send it to crypto block. It deciphered it, decrypted it, and then we put it on queue, and then we took the decrypted packet and we work with it. So the ANA mode allows ODP mode, so which gives a chance to the equipment. It's a mode when first IPsec we just create an IPsec session, and then the packet comes and classifier knows this is IPsec packet, and before it gives it to the application. It's a crypto block, and the application at the exit gets is a plain decrypted or encrypted packet, depending on what needs to be done, and it then can send it outside immediately, right away. So the speed is very high, because everything is done the way it should be done. Then there is this project, Open Fast Path. This is IP stack on top of OpenDataPlane. That's another project which is on openfastpath.org. It's there, and the idea behind it is that so that it works in two modes. So it can take any application from it and Jinx modify it so that it would use IP stack FP. OFP will use under it ODP and OpenDataPlane, and will have a very good performance improvement. The second option is a library net wrap through LDP load. We load it before the application. It determines the system's challenges for the network, and works, does not change the binary version. The main contributors of the project, the companies that you can see on inside the ring, and so then some companies outside that contribute as well. So that's not sometimes they change places. Now just we know some implementations of ODP. that I collected in the catalog, download catalog. So then you can just, using the link, so you can find all these presentations. And so how can we, so we'll be happy to see everyone. So we do have the mailing list and the site, negotiations on this kind of Skype type meetings we can organize. So dataplane.org, so we can organize up to 3 o'clock UTC, which is 6 o'clock Moscow time, every Tuesday. So then the project was organized by another non-commercial organization and financed by the members. When members determine the strategy, priorities for project, and they pay fees to support project maintenance. That's about it. I think that I have not exceeded my time. Any questions?
Perfect timing, in fact. So are there any questions? We have time for some. Down there. If you could reach the microphone.
I have two questions. First question, how do you do the integration with vendors, which SDK closed? And so they give you SDK, or they develop the code integration with you? And the second question, from the viewpoint of performance, how can you compare yourself with VPP, where they process packets through branching, fifth by plane? So how can you integration with vendors is at the level that vendors, so they are linear working group. They're part of this. Before they stabilize an API and goes into release, it goes to vendors first. And the vendors, they say, yes, we can do that on our hardware. If they say we can't do that, or we need it differently, so then they reconsider it, go over it, and then they find a common ground between the vendors. But each vendor does its own implementation of ODP. Because only vendor knows how his equipment works, and so which is a binary blob as a product or open source. Is it binary block open source? No, they upload it themselves, or they either sell or open source, just public domain. So they open it up for everyone. So the project is open, but since it's a new project. So they just keep it proprietary right now, but it will be open. Then VPP, vector packet processing. VPP works on DPDK. It's a lower level layer of DPDK or ODP, and it works a little bit higher. And so we have implementations of VPP for ODP, VPP for ODP. But VPP had a problem because they allegedly the project was not tied to DPDK, but it was using DPDK structure as some private data. It's stored in certain packet. Not all hardware packet. Not all vendors can do that. Can touch header of the packet, and they cannot store it there. So we had a solution that worked well in the implementation of ODP over DPDK, ODP, and then VPP, and or some ODP implementations that they can do it. But to address it properly, so we needed a fix, a DPP fix. I don't know this fix got there or not, and so but the job has been done. It's a hardware job.
What else at the microphone? Oh, maybe one more. So time for one more question.
Направо посмотри.
Yes, here. I'm here. Hi, Gleb Befit. Two questions. When this demag DPCI slide, you said DPDK is it's limited by the speed of the bus. So you send the packets not through the bus, but something else, depending on what kind of hardware we use. For example, if in Freescale they have no PCI, they have their own bus, and it's called DPA2, the name of the bus. And Kalin, I think in new chips, they have their own. And I did this slide. Why I showed this slide? Because PCI has limitations. So that's it. I got it. Now, second question, and the Pro XDP. XDP is a good thing. So patches. Now. I understand that they agree that from 11 patches, 7 will be added to the core, and so patch Intel will be left for the processing IFXZP, so they will be left out for improvement. And so good ideas, but I have not tested it. But I have DP before it. They did it. We did something MDEF. They did MDEF, MVideo. Produced the framework whereby you can take graphic drivers, PCI drivers, and map it in the virtual machine, and then use it there. And we did the same, but for the network devices, and it worked pretty well and fast. And so the idea was, if what with DPDK, we had to rewrite the network driver completely, visor space using UIO or FIO completely. But using this MDEF, you keep your Linux core driver with statistics, with all the tunings, everything tools, and use only a little RxPP function. So RSPP, which would meter space, so will be sending you packets, and so RSDP resolve the same issue, but at a generic level. And for Intel, it works well. For Intel, Linux kernel, the community tries to find a general case where it can be used not only for Intel, under Intel, for Intel equipment.
Thanks for this one. We're out of time for this talk, and I know the next speaker's got an appointment at the airport. So, so I'd like to, everyone, please thank Maxim for the talk.
Спасибо.